So this is a video where we should explain induction. As usual, you should first have a look at the previous videos to be able to understand what is coming in this video. And okay, so we will start now. First, we should imagine this electron, which are constituted about Daons, which pointing radially outward from the right-hand rules. And so if you put an external electric field on top of this electron, then the electric field is defined as going from plus to minus, which means that the rotational axis of the Daons, or the electric field lines if you prefer, will be bent in the direction opposite to the electric field. This will lead to a rotation of the electron, a right-handed direction of the rotation in the direction of the electric field. Okay, so and this is proportional to the order which we have defined earlier. Now, if we now take a look at an electron which has a velocity, no electric field, nothing, just a velocity relative to the free Daons, then again you have a deformation of the surrounding Daons, as we have already seen, and you get that the Daons are bent, rotational axis of the Daons are bent in the direction opposite to the external flux. And you have a very similar field lines as for the electric field. In fact, if you have that the order is exactly equal to the speed of the electron divided by c, then these field lines are exactly equal. And this is an important point. So now, if you have that, earlier we said also, we showed that the velocity of a shell around an electron is equal to the velocity of rotation of the same shell. So now, if you add, for instance, an electric field, then the inclination of the Daons rotational axis, or the field lines, will be different than it would be in case of the velocity. I mean, you have a mismatch between the inclination of the Daons, because you don't have that the speed is equal to the rotational speed anymore. This leads to an inclination of the Daons in the transverse sense, as you see in this figure, and this induces an electric or an acceleration in the direction of velocity, and this is the induced electric field. Such an induction or such electric field, added electric field, can appear in various scenarios. For instance, if you put on an electric field on top of an electron, this gives a permanent mismatch. That is to say, you can never have that the velocity of the electron is equal to the rotational speed, because the electric field is always there to bend give an extra bend to the Daons. So there you have a permanent mismatch leading to an acceleration of the rotation of the electron, so the increased magnetic flux around it. This is what you see in the classical equations for induction. So, and the same thing, if you move a coil, for instance, in a magnetic field, then you must have the relative velocity between the electrons within the coil and the free Daons surrounding it. So also the movement will have to be added to the velocity of the flux. So you have this different properties. Then you have if you add a magnetic flux around the electron, then again the electron will bend its field lines. And if you just put the constant magnetic field, it just will adapt its velocity, and you don't have any specific added induction. But if you add a variation to the magnetic field, so the flux is varying in time, then there will be a mismatch again, and you have a bend of of the Daons in the transverse direction, producing again an induced electric field. So we have this equation that tells you how this works, and this should be developed on a conductor and a coil, and that's the classical textbook thing. So you get the correct classical coil equation. So we should say also here that you cannot change the velocity or energy of an electron if your flux is perpendicular to the velocity of the electron. You only have a bend of the trajectory, you displace the electron, but you don't add any energy or something like this. But if you have the flux going parallel to the velocity of the electron, then you will again disadapt the velocity of rotation and velocity of the electron, and you have a transverse bend, and you induce then an acceleration parallel to the velocity. So this is induced electric field.